Vulkanisar. Today I will speak about Ionia dilemma. This is sort of the main statement, the main working tool of commutative algebra. Essentially, what we did before in this course, we did a bit of Goulart theory, this kind of integral closures, and a bit of classical algebra like Noetherian rings. This is, of course, part of commutative algebra, but you can find it in the book of van der Waerden, which is just, it's called modern algebra, but now it's, of course, classical algebra. And when you start working with commutative algebra, you immediately arrive at two main constructions, Nakayama and completion of rings. And essentially, these two constructions solve most of problems from commutative algebra which can occur in practice. So Nakayama is really important, and this is the central lemma which you use all the time. And one of the questions you can try to ask is the following. Consider an ideal, like a maximal ideal or just any ideal, and let's take all its intersections. So you have A ideal in the ring A, and then you can consider intersection of all powers of this ideal. And you want to prove that it is zero. This is called Krull lemma, and it is true for Noetherian rings, but it's really hard to prove. You can try to do it as an exercise. Well, you would be able to try to do it without Nakayama lemma. It's not really, I couldn't do it when I was a student. So it takes really amazing work of Nakayama and Krull who did that. For example, this is clearly false for smooth functions which are non-Noetherian. Indeed, let's take the maximal ideal, M maximal ideal of a point, ideal of x in R, and this mx is a maximal ideal inside the ring of smooth functions on R. This is precisely the ideal of all functions. Well, they had zero, but then m power k is mx power k is ideal of all f such that f prime k times, well, k l times in x is equal 0 for l is equal for l equal 0 1 dot k. So if you have a functions which have all derivatives in 0, it belongs to this intersection. So if f prime fk prime in x equals 0, f belongs to intersection of m power k x. So this is an example of a non-Noetherian ring such that intersection of all powers of a maximal ideal is non-zero. Another probably easier example is continuous functions. If you have a continuous functions in C0 of R continuous functions, you can take a composition of a function f from R to non-negative R and root It is well defined. In fact, a root of odd power is well defined for all functions. So you can do this. This well defined. If p is odd, this continues. And this means that if you have f belongs to maximal ideal of 0, then f is, you take root of power p of f power of f and raise it to the power of p. So this means that f belongs to maximal ideal of 0 power p. So this implies that intersection of maximal ideals of 0 power p is just maximal ideal of 0, or any x, for continuous functions. So this is an example, again, an example of something which lies outside of this Noetherian ring, and you can't apply the Krull theorem and Nakayama, which I'm going to explain now, are not valid in this situation. Okay, so before I state the lemma, let me remind you a definition. If you have M a model, M, in fact, you don't need that M is torsion free. If A and A is a ring without zero divisors. F is torsion free is for each A inside the ring A is non-zero, and for each M inside the model, also non-zero, AM is non-zero. This is the notion of torsion free. In fact, we don't need, and Nakayama lemma in this one of the forms, which I'm going to state now, says that if you have lemma if M is torsion free, is torsion free A model, and then you have an ideal A inside the ring A, and AM is equal to M. This implies that M is equal to 0. So in particular, if M is your ideal, its square is never equal to itself. In particular, the intersection of all powers of your ideal, of course, it satisfies. So if you have intersection of all powers of some ideal, this is the same as A multiplied by this intersection. So if this should be 0, because this is an example of an ideal such that you multiply it by, of a model which you multiply by ideal, you obtain the same model. So it has to be 0 by this lemma. In fact, this is very weak. You can make it stronger. So the statement I am going to prove is stronger. It's better than, yeah, I wrote here torsion free. You don't need torsion free. So now I will prove the following version of this lemma. Then I would prove it even stronger. So this torsion free, it's an error. You don't need it. So you have a Noetherian ring. It should be also Noetherian. and then M finally generated. A model. And I would, I make an assumption which is similar to Rosenfried but weaker, that annihilator of M in A, it's a set of all A inside the ring A such that A M is equal to 0, and I assume that it is 0. And then then if A M is equal to M for some ideal A inside the ring, then M is equal to 0. So we slightly weaken this assumption of having torsion free. Okay, so let's start with the proof. And step 1. Yeah, I am assuming that the annihilator of this model is empty. This part of the assumption. This is definition, and this is assumption. Thanks. Okay, so step 1, I want to say that endomorphism model is finally generated. So I left it as an exercise. What do you think? Yeah, so we write generators, M1 dot Mn. Yes. Yeah, so you can express each endomorphism by a matrix, and matrix is finally generated. Yeah, except that since there are some relations between generators, then this matrix should be also. Yeah. So it will be a submodel inside the matrices because you have to keep the relations. So and A of M is a subset in matrices. E n. Good. Now we have step 2. So we consider for each phi inside endomorphisms, we take the algebra generated by this endomorphism. It's a ring. It's a commutative generated by phi and finally generated. Generated because this model is finally generated, and our ring is Noetherian, so every submodel of a finally generated model is finally generated again by Hilbert-Bayes theorem. Okay, and then we had something about these finally generated rings last time and before, namely that if if A of phi is finally generated, this implies that phi is a root of monic polynomial. Phi n is sum of A I from I equals 0 to n minus 1, phi phi I. So it's up to n minus 1. It's clear, right? Because you just add phi n, at some point it belongs to this model because the model is finitely generated. So step 3. And it is, I want to, so the idea is that you can treat the endomorphisms as matrices and speak about their determinants. It's slightly, it looks like a bit of cheating because the matrices are not endomorphism. It's hard to define determinant and so on. So, but we still can do something about this. So if you have phi inside endomorphisms A of M, you can express it by a matrix, like we just discussed before. So phi can be expressed by a matrix Aij. Of course, this matrix is not unique because our generators, there could be relations between them. You can always add extra generators, so even the dimension is not unique. But still, you can define characteristic polynomial. As just determinant of T identity minus A. Where T is a variable. So, it belongs to polynomials in variable T with coefficients in A, like the matrix. Okay, I'm going to apply Cayley-Hamilton theorem, which says that if you have A, it's a non-trivial theorem. So step 4. So it looks like a tautology, but in fact, if you try to prove it as a try to treat it as a tautological statement, even over vector spaces, it will fail. It's still true with this non-trivial proof, which you can find in textbooks of linear algebra. So what you have is, if you plug this phi in the characteristic polynomial, consider it as an endomorphism of M, it will be equal to 0. So it's better to write here phi and here of T. So it will be phi here as well. Okay, so how you prove it? You just do it in, you prove it in free model. It will be true. And then it will be, of course, true in the quotient of a free model by, because it's a quotient. If something is 0 in the model, it's true, it's in its quotient as well. So this gives this vanishing for any model not necessarily free. Though, of course, it's not trivial because Cayley-Hamilton is non-trivial. Okay. Yeah, so to make it more rigorous, of course, it's easy to see over a field because we know that in a vector, I mean, it's true for a vector endomorphism of vector spaces over a field. So it's immediately true when your ring has no zero divisors. So in fact, I think I did this assumption in the beginning, but at some point we shall drop this assumption. So it's better to have an argument which doesn't rely on having no zero divisors. To do that, you notice that your ring is finitely generated. So it's Noetherian, finitely generated. There are ways. At the moment, I can't remember because I remember that it's hard, but we had a textbook. It's not easy. No. It's highly non-trivial. Though it's the statement is tautology, but you need to do something. I think what you do is you pass to Grassmann algebra, and some manipulations of Grassmann algebra still give this statement, though it's non-trivial. We can discuss that later. Okay, so we have this characteristic polynomial. We know that this is true for vector fields, for vector spaces over a field. Then you can prove it for polynomial fields, for polynomial rings over any field, because the polynomial rings are have no zero divisors. Then they are true in the field of rational functions, they are true over polynomials. And then you obtain that any finitely generated ring is a quotient of polynomial ring, so this becomes true also in the quotients. This is how you prove this Cayley-Hamilton for endomorphisms of a model. So you pass to a free model over a polynomial ring. You take a quotient of polynomial ring by some ideal. You obtain this statement in this quotient ring, and then you pass from free model to any model by taking a quotient again, and they'll still be true. Just from the classical Cayley-Hamilton theorem over vector space, you can obtain Cayley-Hamilton theorem for endomorphisms of a model. It will be still true, though. Yeah. Okay, so now we have step 5. And in step 5, we apply to identity map. The point is that, of course, in vector spaces, identity map has only one representation, because you take a basis and then it's identity in the base. Not anymore, because now we are in models, and the ways you can encode that endomorphisms are many of them, because you can choose your basis in many different ways. So let's do any representation of identity by a matrix. And then you would have that characteristic polynomial of this matrix applied to identity is 0. And then if you write this characteristic polynomial in, if you write it as t power n plus some ai t power I, from I equals 0 to n minus 1, this would imply by the by the step 4, this would imply that 1 is equal to minus sum of ai in and of m. However, this is the moment we use the annihilator assumption. So annihilator is 0. This implies that A sits in endomorphisms of M, just the A identity, X non-trivially. This is the way you put A inside endomorphisms. It's precisely that this map is injective is precisely this what is written there. So any element of A acts non-trivially on M. Multiplication by this element is non-trivial. So this gives you this map from A to endomorphisms. You just multiply element of A by identity, and you apply an endomorphism which is non-zero. Clear? Good. Okay. Now, this relation, then 1 is equal to minus sum of AI is true in A. So in step, before it was true in endomorphisms, but now endomorphisms contain A, so this is true in A as well. And we can finish. Now the last step is very straightforward. Suppose you have your ideal A multiplied by M is equal to M. Then all coefficients of this matrix Aij, which is identity, can be chosen in this ideal. Indeed, every element Mi this is your generator, can be expressed as a sum of other generators times elements of the ideal. So this is the way you express the relation AM is equal to M. So Aj, let's call it Ij. Aij is equal to, belongs to this ideal A. Right? These are generators, and these generators expressed through elements of the ideal. But this is the matrix of identity map. So Iaj is the same as identity on M. And then you take the determinant of T identity minus this matrix. And this is a monic polynomial, Tn, plus some. Now all elements, all entries of this matrix belong to the ideal, so these coefficients will be in this ideal. Ai belongs to this ideal A. And we apply step 5. We obtain that 1 is equal to minus sum of AI, which is impossible because this is an ideal. It can't contain 1. It's a non-trivial ideal. So this is impossible. Impossible. And this means that AM is never M. If it is M, then it is 0. Okay. So we're done with Nakayama. Are there questions?
So there exists a shorter proof when they start to you just have to formulate your theorem using the notion of maximal ideals and just factorize to your mean by the maximal ideal.
And
And then you can consider the modular
Yeah, but where do you use notoriety? It's definitely false without notoriety. I gave you several examples. But this the argument doesn't seem to use notoriety. I don't know. When I was a student, I spent like a couple of months trying to prove it. I tried to prove Krull and this lemma by myself because I didn't believe that this argument with determinants can be applied. It looks, I mean, it's linear algebra, and then you somehow try to apply it to vectors, to models over a ring. I thought it's unnatural, so I thought I would be able to find a better proof. I don't know. I never saw any proof different from that. Well, there could be worse proofs, but more like better proofs I never saw. This is standard. I don't know, maybe there exists better proof. I'm very interested to know. But this is what you find in A.T. MacDonald, in Van der Waard, and whatever. I expect that this was actually due to Krull, because Nakayama was a student of Takagi, I think, who was a student of Hilbert, and he was like advisor of pretty much every Japanese mathematician in 30s, 40s, and 50s. He was a specialist in class field theory. He did some very good work in class field theory, and then he returned to Japan, wrote like all Japanese textbooks in all math, and became an advisor for a whole generation of Japanese mathematicians. But Nakayama was much younger. You see, he was born in 12. I don't remember where he proved this lemma, but I think it was in 40s. And I expect that Krull did his work probably even earlier. At least he is much older than Nakayama, but probably these arguments were very unclear. Krull was quite great and important. He did not only this work, he did like half of the, since M. Noether, he did most of the work in commutative algebra. He defined dimension and so on and so forth. For ring, the ideas of depth and dimension of a ring are due to Krull. And he was advisor of many people such as Zorn, the guy with Zorn lemma, and our colleague in IMPA, Carlota Stur. He was his advisor as well. And I think many other, he visited Brazil a lot, so at least most of the pictures you can find in Google of Krull are from here. Okay, so we can now prove, but I told that to you already, Krull lemma about intersections. So if you have an ideal in a ring, you take all its intersection, it is 0. But I will just repeat it. Krull if you have A inside A, an ideal, A Noetherian, without, well, you don't need 0. Without Z divisors, assumption can be actually dropped. But anyway, so then, but Noetherian cannot be dropped. Intersection of all powers of this ideal is 0 because A times this intersection is the same intersection. So it's not hard. Yeah, but now I will state a version of Nakayama which doesn't need the assumption that we have no zero divisors. What torsion free? Because it's without zero divisors. This is a ring without zero divisors, but in fact you don't need it. You can prove it for any Noetherian ring just doing some localization. It's an exercise.
It's strange. Why doesn't it work just for A or an ideal? Because an ideal is a module.
It works. This is what I told you. I mean, what's the question?
No.
This is the proof. It works for any ideal. Yeah.
So you have a module that is torsion-free.
Mm-hmm. No. Here you have, for Krull theorem, you don't have any model. You just have an ideal. And this for Nakayama. And again, you don't need torsion-free model. You just need that it has zero annihilator. But in fact, you can drop entirely the torsion-free annihilator assumption, even the assumption that it has no zero divisors. So I will state that it's slightly less pleasant statement, so I stated it after I proved, but the proof is the same. So it's a version of Nakayama lemma. You have Noetherian ring and finally generated a model. M finally generated. And then you have an ideal such that AM equal M. A inside A an ideal such that AM is equal M. Then 1 plus A of times M is equal 0 for some element A inside this ideal. And the proof resides at step 5 of this proof of Nakayama lemma which I gave. So the only place we use the assumption something is torsion-free or that annihilator is 0 is step 5. You realize identity as a matrix with coefficients in A. You can do that over any ring for any finally generated model. Then you write its characteristic polynomial, and it's equal to it's written like that in endomorphisms of M. In endomorphisms of M, this characteristic, I mean, it's a you think of this. Of course, it's a matrix. It's an element in A of t, but you realize you put it inside and A of M. And inside this end of M, it acts by 0 on M by Cauchy-Hamilton theorem. So in step 5, so the proof is the following proof. In step 5, we proved that this polynomial P of applied to 1 is 0 in endomorphisms of M, where P is determinant of T identity minus the matrix Iij, where Aij belong to this ideal. This is something we already had. So P of 1 is this is 1 minus sum of AI. Yeah. P of 1. P of 1 is 1 plus sum of AI. And it acts by 0 on the model. This is precisely what is written there. So it's not a big deal. It's actually the same statement, just modified. Am I clear? Clear? Please ask questions. I would really appreciate it. Okay. So everything gets much better over local rings. So what is a local ring? It's another super important notion in commutative algebra. So local ring is just a ring which has only one maximal ideal. But the good thing is that you can always obtain them starting from any prime ideal. So definition, suppose you have A is a ring, is called local if A has only one maximal ideal. So let me give an example. Well, the first example is a field. It has only one ideal, maximal prime, just 0. It's a trivial example, of course. The better example is the ring Z, where you invert all, so it's better to say it's subring A inside Q of all fractions with with odd denominators. Odd denominators. Then in that ring, let's use some notation for that. So let's call it, so it's a subring inside Q, call it Z of 2. So X, so Z of 2 is all fractions A by B, where B is odd. So all odd numbers are invertible in this ring. So it has a maximal ideal, namely 2. So 2 is maximal ideal. Now the quotient by this ideal is Z by 2. Right? On the other hand, if X doesn't belong to this ideal, so this means that X is A by B, where A is odd. Right? It's not divisible by 2 in that ring. Then X is invertible. So this means that if an element doesn't belong to this maximal ideal, it's invertible. And this is why it is the only maximal ideal. So anything, so in fact we can characterize, this is a good way of characterizing local rings. So remark, A is local if for some maximal ideal M is side A, all x which doesn't belong to M are invertible. No, no, no. Lots of ideals.
No, but if we have an ideal, then any its complement.
Look at that 0 here in that ring. 2 is not in this ideal, but it's not invertible in that ring. So it doesn't work like that.
Probably with prime. You can say prime.
No, it's actually a prime ideal. 0 is prime ideal here because it has no Z divisors. No, this is precisely, so the intuition is, which is like prototypical maximal ideal, is C with formal power series. So why it is local? Again, consider a formal power series. So the maximal ideal is generated by T. T is maximal ideal. And now take something which is not divisible by T. This means that you have a power series, formal power series, A0 plus A1T plus A2T squared plus and so on. And A0 is non-zero. I want to invert that to check this assumption. So for that, I take 1 over A0 multiplied by 1 plus R, where R is equal to sum of AI T. So this is F, and I write this as that, multiplied by A0 minus 1. The important thing that the sum R power I minus 1 power I converges. Well, it's well defined. Converges in the sense that it is it belongs to this power series ring, because each term Ri starts with T power I. So indeed, for each term T power D, there are only finitely many terms in that which sum up. So this makes sense in the formal power series. And then you A0 multiplied by 1 plus R, and then you multiply it by this 1 plus R minus R plus R squared minus R cubed, and so on. This is well defined, this is well defined, the product is well defined, and this gives you A0. So this means that this function is invertible. Okay, so this is the prototypical local ring is the ring. The same argument works for the ring of germs of functions, which is very similar to formal power series. It's just not formal power series, but convergent power series. Convergent in some radius. Or holomorphic, smooth, continuous, doesn't really matter. So consider X inside M, and let's or Mx, the ring of germs. Of germs of, say, smooth functions, or continuous functions on M in X. What does it mean? Two functions have the same germ if they are equal in the neighborhood of X. This means that they have the same germ in X. And you consider the space of the ring of germs, the ring of equivalence classes of such functions. This is something we had in handout number 6, I think. Yeah, handout number 6. We had the ring of germs. Okay, but now if you have f inside this ring of germs, OMX, and f of 0 of x is non-zero, then f is not equal 0 in some u containing x. This is because the set of zeros of a function is closed and the complement is open, so f is invertible on u. So it's invertible inside the ring of germs because germs, I mean, the restriction of f is invertible on some open set. That means that it is invertible inside germs, because you can always restrict all germs on the same u or some smaller set where it will be invertible. So if this another, this actually it explains the term local ring, because it's really local in the sense of having I mean, it has the same properties as the ring of germs. This is why it is local. Okay, we can make a break for 5 minutes. Temos intervalo para 5 minutos. Okay, so we started with the definition of local rings. We had some examples, and we have this nice characterization. Okay, if it's why this characterization works again. So the characterization says that if A is local, if there exists maximal ideal such that all elements which don't belong to this maximal ideal is invertible. This means that all ideals inside your rings are contained in that ideal. I mean, everything which is not contained in that ideal is already invertible, so it can't be in an ideal. So it is really a maximal, and it is unique, because all other ideals are contained in that ideal. So this is why such a ring is local. And conversely, if you have a local ring, you have some element which doesn't belong to your maximal ideal, you can have another ideal which contains this element, because we know that for each element which is not invertible, it's contained in a maximal ideal by its own lemma. So we would have a maximal ideal which is not contained in our ideal unless this property is true. So this uniqueness of maximal ideal is equivalent to having an ideal where its complement has only invertible elements. And this leads to a construction of localization which gives a local ring for each prime ideal. So definition. We had already a notion of localization. You can, if you have a multiplicative system, namely a set of elements which doesn't contain zero and is closed under multiplication, so you have S inside A, closed under multiplication, and zero is not in S, then you can invert, can have can localize A in S by taking all fractions, A by S, where A is inside ring and S is inside this multiplicative set. It's well defined. But this is something we already mentioned several times. So this is standard. But now, suppose we have a prime ideal. P inside A is prime. Then A without P is a multiplicative clause. This is actually part of the, I mean, it's the same as prime. What does it mean that ideal is prime? Is that all elements which don't belong to this ideal, a product of such elements is, again, not in this ideal. So this is, and of course, it doesn't, since 0 is in P, this doesn't contain 0. And then you can localize. So localization of A in this set, A without P, is called localization of A in P. And I claim that it is actually maximal. So claim localization of A in P is maximal. Proof. Of course, all x which are not in P are invertible. And we apply this remark. Okay, so this is, so every time you want to solve some problem in commutative algebra, you just localize over an ideal, and it's solved by application of Mikhail. Well, maybe not always, but it's like 90% recipe for most of the problems. Okay, now let's do an application of Nakayama for this particular situation. So claim. Yeah, by the way, there is something we already had mentioned a couple of times, but definitely had to mention this again. So claim a localization of Noetherian ring is Noetherian. Proof ideals of localization sit in the set of ideals of localization, subset of all of localization of A for any localization, for any immutable set, is subset of the set of ideals of A. This is something we already discussed. It's not hard. It's very simple algebra, and this was such a result before. So this means that, I mean, okay, yeah.
And then there's slight problem that those are sets of ideals in two different rings. So
Yeah. You have your A. You put it inside this localization. And for each ideal I here, you take its intersection I intersected with A. And it gives you an injective map from there to there. Just from ideals in there to ideals in there. This is something we had. In fact, I can repeat a proof.
Also, we can think about the localization like a quotient by ideal 1 minus.
Yeah, but quotient doesn't work with this that well. I mean, for quotients, you don't have this bijection.
No, I mean just apply Hilbert's theorem to consider A as polynomials and then.
Hilbert don't work well with localization because localization is not finally generated typically.
I think we will look at there's like very general dilemma that if we have a subjective morphism of two rings, then ideals in one ring are in one-to-one correspondence with ideals.
Yeah, but you can't apply this theorem here because you don't have any subjective morphism there. It's injective.
But but you can just consider just add one variable t.
Yeah, but it's infinitely many. Yeah, you're right. This is one of the ways of doing it. But we did it straightforward without this, without Hilbert Neustein, that's without nothing. So I can remind you actually, it's probably worth doing. So you have this embedding A inside A S minus 1. You have an ideal M here. You take M intersected with A. And I claim that M is equal M intersected with A times this localization over A. What does it mean? It means that you just add denominators. I mean, you take this intersection, you add denominators, you obtain this ideal back. So this is why it is injective. Every ideal in there is obtained from an ideal in A by taking localizations. In particular, if you have chain of ideals, in localization, this gives you a chain ideals of A. If it's infinite chain, you get infinite chain in A, which is a contradiction with Noetherianity. Then corollary, localization of Noetherian is Noetherian.
It was a problem in your first list.
Yeah, thanks. This is its solution. But what is useful that now you can apply whatever you know about Noetherian rings to localizations, even typically they're not finally generated. So if you think of just of some simple ring like just the ring which I discussed before the break, which was Z localized in 2. Maybe we should write it now like 2 minus, yeah, it's localized in 2 in the sense that we added all odd denominators. This is not finally generated, because finally generated with subring of Q would have only the denominators will have only finally many divisors. I mean, if you have finally generated ring of Q, this means that you added like A1 divided by B1, A2 divided by B2, A3 divided by B3, and then denominators of all the elements generated by these numbers will have divisors which are divisors of B1, B2, B3, and so on. So there will be finally many prime divisors of all denominators of finally generated ring. And here we have odd numbers in denominators, so this is not finally generated. Another example is you can take C, just polynomials of T, and then localize by all P which have you localize by all P which are not divisible by T. So you localize by all P minus 1 for P of 0, non-zero. P of, you invert all polynomials which are, so it will be like rational functions which don't have poles in 0. It's also local for the same reason. I mean, it has maximal ideal, which is rational functions which vanish in 0, and all functions which don't belong to this ideal are invertible in that ring. Again, it's not finally generated for the same reason. You have lots of denominators. So this kind of rings, they are Noetherian but not finally generated. Okay. Yeah, localization is local we proved, and now there's a version of Nakayama lemma. So you have A is Noetherian local, and you have M1, M2 finally generated A models. And you have phi homomorphism. Morphism of models. And suppose that phi induces surjective map. Yeah, local, and M is maximal ideal. And phi induce surjective map from M1 quotient by M1 quotient by maximal ideal to M2 quotient by M2. Then phi is surjective. This is a very important result which is used all the time. I mean, so let's prove it. So proof. I define M3, which is cokernel of phi. And if you have any element x in M2 is in phi modulo M maximal ideal times M2, right? This is because it's in surjective modulo maximal ideal. then M3 is equal to M3. Every element M3 is belongs to maximal ideal times time itself. Times M2, but this is the same as maximal ideal times M3 because it's M2 surjectively maps to M3. And the Nakayama implies, in that strange form I gave later, I mean, it's for not rings which are not necessary without the divisors, gives that 1 plus M times M3 is equal to M3. Oh, sorry, is equal to 0, of course, where M is an element of this maximal ideal. Right? But this is invertible. Because all elements which don't belong to maximal ideal is invertible, and this implies that M3 is equal to 0. We're done. Should I repeat? Sure. Look, we have this map phi. Define M3 its co-kernel. For each x in M2, its image x belongs to image of phi up to maximal ideal. This means that n times M3 is equal to M3. Indeed, you take an element M3, you take its pre-image in M2, it will belong to maximal ideals plus image of phi, then its image belongs to maximal ideals times image of M2, so that it belongs to n times, you obtain that n times M3 is M3. Good. We are in a situation where you can apply Nakayama lemma, and it will give you that if you have this property, then this is also true. 1 plus m times M3 is equal to 0, where m is an element of maximal ideal. Okay, and this is invertible. So you have M3 multiplied by invertible element is 0, then M3 is also 0. You can just invert that and multiply it by its inverse. You obtain that M3 is 0. Okay, this is the argument. Let's now, okay, I'm now going to apply that to a bit of geometry. And so I'm going to repeat the definition, which we already had several times in these lectures. So the first observation is sort of trivial. The tensor, if you can increase the scalars, then you do it with finely generated model. It remains finely generated. This is trivial, so let me write this remark. So if you have a ring homomorphism, R times R1 is ring homomorphism, and M is finely generated R model, then N times R1 over R is finely generated R1 model. This is trivial. I mean, if you have generators for M, you just take the same guys and call them generators for M times R1. They will generate. Is it clear? If you have indeed this, if you have a ring homomorphism, you have finely generated R model, then its product is finely generated as R1 model. So if you have x1 dot xn generate M, then x1 times 1 dot xn times 1 generate M times R prime. R1, by definition. Okay. Yeah, so now finiteness. If you have x goes to y, and or x is finite generated as OY model, this f is called finite. And or x is called finite extension. Integral extension, sorry, integral extension. Of OY. So it's something we discussed last time when we said that, okay, if you have finite extension of something which is integrally closed, then integral closure will be finite. This is precisely the situation which I'm now describing. Okay. Now the theorem which we had, it was in, I think, lecture 10 and 11. And it's a theorem, but in fact it's almost one line, so it's probably a claim. So theorem. Suppose you have f from x to y finite map, then f minus 1 of a point y is finite. And the proof uses that f minus 1 of y is spectrum of OY, OX, sorry, times OY quotient by maximal ideal. So my maximal ideal of the point y, so it's my, and this you take a quotient by nilpotence. This is something we had, right? It's actually true for any sub-scheme, any sub-variety. You can do the same. Take its quotient by its ideal, tensor multiply over OY with this quotient, and take quotient by maximum by nilpotent ideal. This will give you this hybrid product, which is in that particular case is just preimage. But then this is Artinian. It's Artinian ring of Artinian ring is finite, because this is direct sum of fields. And direct sum of fields has only finitely many maximal ideals, or prime ideals. Okay. So this is something we had. Should I do more or just go on? Clear? Good. Okay. But in fact, the stronger result is true. Yeah, so you can't expect that in that situation, you can't expect anything better. Let me give you an example of finite map, which is definitely not surjective. You have, say, a line goes to a plane. So you have plane corresponding C of x, y, and the line is C of x, and your corresponding map of rings is just a quotient by x is y is equal to 0. So this is the map. So you take a map O of x, y, and this is a quotient by the ideal generated by y. Yeah? Sorry, you had a question. So you take just quotient by this ideal. Yeah, it's clearly finite. because this quotient is a finite model over that. I mean, it's generated by unity, yeah. So this is, the quotient is always finitely generated as a OXY model, but the preimage of a point is empty set. You can't expect it to be surjective. This is a situation when you can expect finite maps to be surjective, but this is like one of the stepping stones in a bigger pursuit of raising and lowering the ideals under finite maps. But let me state this first theorem, which is like first step in that theory of Cohen and who else? Cohen and Seinberg, thanks. Yeah, Cohen-Seinberg theory. So theorem. Suppose you have f from x to y is finite and dominant. Then f is surjective. And a posteriori, by this theorem, it's n to 1 map, so it's k to 1 map, where k is, of course, not constant. It's just finite set to 1. So it's all preimages are finite and non-empty. So this means that you can't have a situation which you always have in bigger generality, and you have something like C without a point goes to C. This kind of map, it corresponds to a map from C of t to the Laurent polynomial, C of t, t minus 1. So the Laurent polynomials have spectrum this, and this has spectrum that. This is not a finite map, because t minus 1 is not a root of any monic polynomial. So, and this is why it is not surjective. And this theorem, so let me explain why it is important, because there is a whole set of theorems which explains that if you have a prime ideal you have a finite, like, integral extension from a ring A inside of B. So the idea is if you have prime ideal there, it can be, if you have prime ideal there, it restricts to prime ideal there. But the converse is also sort of true. If you have prime ideal there, it's a restriction of finitely many prime ideals in B. So there is a certain n-to-1 correspondence between prime ideals in B and in A, and this is an important part of algebraic geometry, commutative algebra. For instance, how you do define dimension, for instance. You do it as follows. You do this finite type map from polynomials from the ring. So you have a map from X to finite map to Cn. Well, you need some normalization, but this is doable. And it corresponds, of course, to a finite extension from polynomials to your ring. So you have polynomial C of T1 over Tn are embedded into it. This is finite. You have some ideal there, which corresponds to, and it will give you an ideal here. And there will be like 1 to n correspondence between ideal there and ideal here. And then if you want to define things like dimension, you can always reduce to ideals there. Because the typical definition of dimension is the following. If you have prime ideal, you consider a chain of prime ideals contained in that ideal strictly. Like you have P contained in P1, contained in P2, this, and you take the chain of biggest length of that type, and it is dimension of P. And from that construction, you immediately obtain that you can reduce all question of dimension to just Cn. So it's an important application of, let me prove it. So I wanted to prove that finite dominant maps are really dominant means that the corresponding map of rings has no zero. It has no zero. I mean, it has no kernel. Okay, so let's prove it. Yeah, we can erase everything probably. Okay, so I'm proving surjectivity. Step 1. So if we can always restrict to irreducible components or just assume that everything is irreducible, because in fact for varieties we can define finite maps. For rings it's not very interesting. So if we assume that all our varieties are rather restrict to reducible components. So you can assume that y is irreducible. Then x is also reducible because dominant map to something irreducible. If you have dominant map from x to y is irreducible, x is also irreducible. This is something we already had. X is irreducible.
But why this subjectivity of this map not follows from the dominantness?
Because we have this kind of map. It's clearly dominant, right?
Yeah.
But not surjective. You need to use finiteness somehow. Otherwise, it won't work. So it's really important because without finiteness, it won't work. And when you do this kind of dimensional reductions, you will always reduce to finite maps. Okay, so we'll take x is equal, or x is equal to b, or y is equal to a, and b is finite. Is integral extension of A, which is contained in B. And B is finitely generated. In fact, if you are interested in a situation where it is not necessarily reducible, you can check it for each irreducible component. You want to prove that on each irreducible component, the corresponding map is surjective, and then it will be surjective on all of them. So you can always reduce everything to reducible components and prove surjectivity component by component. Okay, so we reduced to that case. Let's now do step 2. And step 2 is applying Nakayama lemma. You have maximal ideal of a point my inside A is maximal ideal. So I reduced everything to the situation where or x is denoted by b, or y is a. A sits inside of B, and B is a finitely generated A model. Now I start with the maximal ideal in A, which corresponds to a point in Y. And by Nakayama, my times B is not equal to B. Well, B is without zero divisors, so it can't be equal. Well, because it's finitely generated and there are no zero divisors, so it's very simplest part of Nakayama lemma already gives it. Okay, now step 3. And step 3 is the theorem which I just erased that was written there, which says that f minus 1 of the point y corresponding to this ideal is spec of b times over a by maximal ideal of y, and this quotient by nilpotence. Okay. Now what we know is that b over a times my is b quotient by myb. This is something we used, like every lecture we use this observation, right? And this non-zero. So this is a non-zero ring. Its quotient by nil radical is also non-zero because it contains it contains 1. It can't be all nil radical. So this is non-zero. Then this has a point because it is non-zero ring. It has maximum ideal. Maximum ideal is a point. So this then f minus 1 of y is non-empty. Indeed, we have this surjectivity for finite maps. Okay, I think this is it. Thank you very much. So next time we shall continue with applications of Mikhail. With Aplicada.